Hello everyone, Professor Lohit here. Today we're going to see the lecture number 4, temperature stresses. In last class we seen the wheel load stresses. So today we're going to see the temperature stresses in a rigid pavement. In temperature stresses we have the two different stresses. One is the wrap stresses and one more is the frictional stresses. So the daily variation in the atmospheric temperature is causes the difference in temperature between the top of the CC pavement and the bottom of the CC pavement. This result in wrapping of cement slab and consequent development of the frictional stresses, and therefore this is important factor affecting its design and the performance. So difference between the maximum atmospheric pressure during daytime and minimum temperature at the night depends upon the climatic factors and the locations. So the wrap stresses during the day, okay, what happen, the top the pavement of the slab becomes hotter under the sunlight when the bottom of the slab still remains relatively colder than the top, resulting what temperature gradient throughout the depth of the slab So this result in expansion of the what top slab with respect to the bottom. So the maximum difference between the temperature of top and the bottom slab may occur at some period of after at mid-noon. So if the maximum temperature at the top of the CC pavement during the day is T1 degree Celsius and the temperature at the bottom of the pavement at the time is T2 degree Celsius, so the maximum difference in temperatures between the top and bottom of the slab of the temperature differential the day is given by T degree Celsius, nothing but T1 minus T2 degree Celsius. Clear? The temperature difference between the top and the bottom of the CC pavement results in differential expansion of the slab during the wrap, causes it to wrap or a bending we call. Okay, as the wrap resisted by the self weight of the concrete pavement, the flexural stresses are developed at the bottom of the slab at the interior and the edge locations. So the of the pavement slab at the corner the slab tends to wrap downward. So at this corner is what happened, the slab wraps downward. This is at the mid-noon. So what it vice versa in case of the midnight, that time the temperature of the bottom will be more and the top will be the less, because the heat absorbed by the earth is given back to the atmosphere. In those conditions the heat at the bottom layer of the surface is going to be more compared to the top, because it's cold, so top surface will be cold. So in that it will be the reverse formation. So midnight will be wrap at the bottom and midnight it will be reverse way. This is what you call wrapping stresses. Okay, this is what you are going to calculate in a further. So as I said, the Westcard worked out the magnitude of stresses due to the wrapping of the concrete slabs at the interior and edge by the considering the effect of what Poisson's ratios and using the wrap stresses coefficient given by the Bradbury. Clear? So that as I told, the temperature stresses developed in the cement concrete pavement is due to the variation of the slab temperature. The variation in temperature across the depth of the slab is caused by the daily variations, where an overall increase or the decrease in the slab temperature is caused by seasonal variations. Okay, in the temperature. Okay, these are the wrap stresses, the daily variations. In seasonal variations of the we come across the frictional. So there in those conditions the two types of stresses are produced as I mentioned due to the temperature variations in the concrete. The wrap stresses is due to the what temperature difference between the top and the bottom of the pavement as a result derivation in the temperature at the locations. Okay, this is the wrap stresses. So in the frictional stress, whatever the you're going to find is due to the overall increase or decrease in temperature of the pavement slab as a result in seasonal variations of the temperature at the locations. Clear? So when you talk about the wrap stresses, the again we got the three formulas. Here I add that the suffix at the what stresses. So if I write only S and I means it's a V load stresses. If I add T there, it's a temperature stresses. Clear? So temperature stresses internal is given by this formula. Temperature stresses at the edge is given by this formula. Temperature stresses at corner is given by this formula. Where again ST is nothing but wrap stresses at interior given by kg per centimeter square. E is nothing but modulus of elasticity of the concrete. Small e is nothing but thermal coefficient of the concrete per degree Celsius. Small t is nothing but temperature difference between the top and the bottom slab in degree Celsius. And here Lx and Ly are the length and width of the slab along the direction x and y directions. So with respect to that, the Cx is nothing but coefficient in the direction x, which depends upon the ratio. Cx depends upon the ratio Lx by L, and where Cy is depend upon the Cy by Cl. The coefficient of direction y depends upon the ratio Cy by L. As I mentioned, Lx and Ly are the length and width of the slab along the x and y directions, where mu is nothing but again the coefficient of Poisson's ratio of Cc, which is taken as generally 0.15. If they are not provided in the problem, take it as a 0.15. Clear? And A is nothing but the radius of contact, and L is nothing but radius of relative stiffness. Okay, this is all about the wrapping stresses. In next class we see the problem that, okay, on wrap stresses. Thank you for patience hearing.